So for today, my hope is to just do some brief things in CAD, and then we're going to walk through selecting a 3D printer. I know some people took this course specifically for that reason, and so I want to make sure to spend time covering that. I guess before we dive into just two quick examples. Does anybody have any general questions on the coursework, lessons 6 or 7? In lesson 6 and lesson 7, we covered freeform. Let's see here, chat. Bill, if you can. Cool. Thanks, Mickey. Lesson 6 was all about Freeform Cad, and lesson 7 was about direct modeling. And I don't know where, I think folks are probably somewhere, just based on looking at the video views, most folks are somewhere at the end of lesson 6 at least. But those are definitely very different approaches to working in the CAD environment. And as you've probably noticed just in working through those lessons, they certainly have their advantages and their specific uses. So freeform modeling is a lot easier approach and maybe more effective approach to making that saw encasing with lots of, and I'll pull it up. Let me screen share. Get this stuff out of the way. So the saw encasing that we made in lesson 6, there's a lot of really kind of complex curvature, ergonomics. If you're trying to make aesthetically pleasing curves, that's not as easily done in parametric modeling, and so Freeform Cad is a nice approach to that. I would say the biggest downside to Freeform is that you don't have a history of all of your steps, and so going back and revising a really complex geometry can be time consuming. Also, when you go to spec this out or like create a drawing, it's going to be really hard to capture, say, the angles and the overall geometry that you want using like your standard drawing template, because it's not made from parametric modeling, sketches and extrusions. Then we did some direct CAD and lesson 7, and that's kind of a bridge between freeform and parametrics. It's not quite freeform, but you also have some functions in parametrics, in that you can go back certain steps, but not all the way. So it has its place as well. Certainly useful, but by and large, I would say stick to parametric CAD as much as you possibly can.
Yeah.
I did want to highlight just a few quick things. These came from questions from folks throughout the week, and so I wanted to just hit on them here, and then we'll get into our presentation. One question was from Dana, and that was, what's the point of a fixed or unfixed joint segment point in a sketch? Let me just open a sketch so that we know what we're talking about here. Let's go like this. And if I draw a line, then I can come in here, and there's this fix unfix constraint here. And you can start clicking on things, and you see it changes color, and that fixes the line. And what I haven't used this all that much, and so I did just some reading on this forum, and essentially it's constraining certain parameters about this segment. So by clicking on it, we have defined its location and space, but we haven't fully constrained it, and so there's still certain degrees of freedom just by us clicking fixed that we can still manipulate, like the magnitude of this line. We could go in and change that. And so I believe by using fixed, you still have, say, control over some of those parameters. Whereas if you were to go in and dimension it based off of like your center point, you may not have that freedom. So that was what I gleaned off of this this forum here. I'll send that out to you guys. I don't know when I would ever use the fixed unfixed constraint. I tend to like, to know exactly how something is dimensioned versus just, fixing it in space. But it's a tool nonetheless.
So is that for form or direct kind of work, or I'm not sure I understand.
The fixed, sorry, no, the fixed unfixed, that was not necessarily tied to lesson 6 or lesson 7. It was just a general question, and that would be, that would be more parametrics.
Okay.
And then this question came from Bill, and so I wanted to highlight it. So we're in our model here where we're building our casing. I'll go down to edit. And this was the step where we wanted to flatten the right curve of this on the XY plane so that we could then mirror it across. And I believe one of the steps highlighting, how could we easily highlight all of these segments without highlighting other segments or panels. And so I covered this in one of the tutorials, but if you haven't seen it, we're gonna do it real quick. If you click and drag down and to the left, you're gonna see that we get a yellow box with a dotted blue line, okay? So if I hover over a portion of this component and I click, you'll see that everything that was touching that yellow box has been highlighted. So I'll do that again. So even the panels that are just barely touching the yellow region, they get highlighted and selected. If I instead click and drag down and to the right, we have an orange box with a solid blue line. That's only going to highlight things that are fully inside of that region, not just touching. So if I want to, for example, highlight just that upper left panel, or upper two or three, see, it's just going to select those two without selecting anything else that was touching that red box. Does that make sense? So in this case, we would want to use the orange box here because we're only trying to select the right edge, and we don't want to grab all this other junk. If we try and use the yellow or the yellow box to drag into the left, we're going to highlight all this other stuff we don't want. So we're going to more effectively grab this edge by using the orange box. If you saw how I did that. Not grabbing anything else, just our right edge. And then we went into modify, and I believe it was flatten. And if you did the tutorial, or if you haven't, you're gonna see this in writing and also in video form later. So I'm just kind of breezing through it. Select plane, and then the plane that we want to flatten this curve along, we want all these points to lie on the XY. So come down here to our origin, and you'll see that it flattens right along the XY here. So our part's now ready to mirror across that plane, and we won't have any gaps, say, in our case. So we got Chelsea. Yeah. Great. Awesome. So this was also covered earlier on as well. Thanks for highlighting that.
Good.
Cool. All right, we're going to shift gears now, unless there's any other questions on the tutorials themselves.
I have a question.
Yeah, go ahead.
I didn't get too far in lesson 6, but so this might have been covered, but can you create a design using both freeform and parametric?
Yeah, absolutely. And so that's actually what this guy is here. Let's see. Well, if we go down, we'll see that all these other features here in our history, these are extrusions based off of sketches that we can't actually open up. But, oh, here, if I open up internal mechanics, all of this was used making parametrics. And then the casing that we're making is using freeform. And that shows up in our design history as a form, as a freeform part. So, good question.
Cool.
Yeah, go ahead, Bill.
I was wondering what the difference is between, am I still muted? No.
Oh, you're good.
Okay. The difference between press, pull, and extrude. They seem to do the same thing, as far as I know.
Yes, they do, except for extrude, you have to use a sketch. Press pull can use a sketch or an existing face. So press pull is a form of direct modeling, whereas extruding has to be done based off of a sketch.
And if you're on a sketch, you can still use the press pull, though, I think, right?
You can. So you can use the press pull on a sketch, but you can't use extrude on simply a face.
Okay,
Yeah.
Thanks.
Mm-hmm. Cool. Good questions. All right. So let me grab. All right, selecting a 3D printer. Okay. You guys can all see my screen? Cool, so selecting a 3D printer can be a daunting task because there are, there's obviously many out there. They're all driven in different ways. And so what we're gonna do today is hopefully come up with at least a method for searching and looking at a variety of printers and then choosing the right one based on a variety of parameters that you're gonna set. Let's see. Hold on here. Try this a third time. Okay, so we've discussed this last week. There are many different types of 3D printing. There's just a list of 6 there, and there's even more than that. They all use different methods, but they share a commonality in that they're building parts layer by layer. And the most popular among hobbyists are stereolithography, so SLA, or what we've already discussed quite a bit about, which is FFM or FDM. The main reason that these are most popular among hobbyists is because one, they're the cheapest, and I guess the most straightforward. They're the most plug and play. But 2, they also have, I would say, the widest variety of uses and applications. So for example, direct metal laser melting or selective laser sintering, those are like a pretty niche type of 3D printing that you would use with just a very small number of materials to make, very focused, let's say a focused design. Whereas stereolithography, you can print ceramics, plastics, really anything that you can embed into a resin and then bake out the resin later can be used with SLA. So there's a lot more applications for both SLA and FFM. So that's what we're going to focus on. If you guys are specifically interested about other types of 3D printing, you can certainly shoot those questions to me and I'll do my best to answer them. I'm certainly not well-versed in all of them, but feel free to shoot them my way nonetheless. We already watched the FDM video. I simply put it in this presentation so that when we download it later, it's complete. So we're going to breeze over the video and then watch the SLA video so that you guys get a better understanding of that process. So we're going to jump through that and we're going to watch this. Let's see. Let me share sound.
3D printing technologies create solid parts from 3D models layer by layer. Among them is SLA. SLA stands for Stereolithography, a 3D printing process that uses a UV laser to cure liquid resin into hardened plastic. Upside down or inverted stereolithography is the most common SLA system. Depending on the machine, resin is either poured into a tank by a user or dispensed automatically from a cartridge. At the beginning of the print, a build platform is lowered into the resin, leaving only a thin layer of liquid in between the platform and the bottom of the tank. Galvanometers direct the UV laser through a transparent window at the bottom of the resin tank, drawing a cross-section of the 3D model and selectively hardening the material. The print is built in consecutive layers, each less than 100 microns thick. When a layer is complete, the part is peeled from the bottom of the tank, letting fresh resin flow beneath, and the platform is lowered once again. Originally developed in the 80s, SLA was confined to large industrial machines until recently. Today, desktop stereolithography offers affordable, high-resolution 3D printing that fits conveniently in your workspace. SLA allows for the use of a wide range of materials with diverse physical properties. Whether you're an engineer, product designer, sculptor, jeweler, or dentist, there's a material for your application.
All right. So you can see that it's a little bit different than FDM in its approach, and also obviously the materials that it can print. We'll look at that a little bit closer here. So we won't go through this exhaustively here. You will obviously have access to the presentation. You can take a look at this stuff in greater detail, but I will point out that resolution and accuracy are both much better with the stereolithography process. And this is because the laser spot size used to cure the resin is much smaller. So the laser spot size is anywhere from I think 20 to about 50 microns. And galvanometers, that's the motors that are used to move the mirrors. Those are a lot finer tuned, let's say, than the XYZ motors that are used to control FDM. Not to mention the nozzle diameter of most FDM printers is in the 200 micron range. So you're an order of magnitude coarser or less defined with FDM than with stereolithography. That obviously is going to have an impact on your surface finish. That kind of ties in with resolution and accuracy. If you can resolve smaller points and your printer's more accurate, your surface finish is going to be better. Also on that note, another kind of function of surface finish is how the bond is being made. Okay, so with SLA, you're thermosetting, you're creating a chemical reaction, setting that plastic together, so the bond is a lot stronger, versus FDM, where you're melting a plastic and fusing the layers, via melting and resolidification, if that's a word. So stereolithography results in typically a stronger part with much better layer adhesion, because you're actually curing a resin versus melting it and hoping that as it solidifies, it melts in with the bond below it. Throughput is about the same for both. With fused deposition modeling, your motor, say your print head, it doesn't move as fast, obviously, as a laser, but you're putting out a lot more material at at any given time. And so for that reason, the two kind of are equal. Stereolithography cures a smaller volume, but in a shorter amount of time. So those are relatively equal. complex design, stereolithography has a little bit of an edge on FDM simply because of what we've already discussed about resolution and accuracy. FDM tends to be less expensive than stereolithography for all of these reasons. The components are cheaper, they're more accessible. And so if you're looking to say get started with just with 3D printing, FDM is a great place to start and to get your feet wet at a lower cost. Let's going down the list here. We don't need to hit everything necessarily. Print volumes you're going to see are pretty much the same. So that's if you're looking at one or the other, that isn't going to be a deciding factor. Materials is a big one. So thermoplastics are pretty much the limitation to FDM. You have to be able to melt the plastic so that it then goes through the nozzle and then resolidifies as your part. Whereas with stereolithography, it's a curing process. So you're thermosetting these plastics. In other words, you're applying rapid heat for a really short amount of time, and then it's curing and in such a way that it can't ever be unmelted with heat or with anything else. So you can do, print materials with SLA that are a lot, say, higher temperature resistant. And this is what's really cool about SLA. You can embed pretty much anything into a resin. So let's look at like ceramic particles, for example. And then there are certain resins that you can print with that you can bake out later on or dissolve away. And so what you're left with is a porous ceramic that you've successfully 3D printed. So that's just one example. But with SLA, there's a wide variety of things that you can print with because of the nature of embedding resins with other materials. I will say that they do embed certain PLAs for FDM as well. So you can actually get conductive filaments. So it's embedded with carbon or something like that. You can get wood embedded PLA, things like that. So there are other materials you can effectively print with FDM, but not in the same manner as SLA. Cool. You guys can look at the rest of that maybe later on. Are there any questions about the two? Yes, Dana.
I just have a question about the workspace that they were in. I see the facility requirements for the FDM says air conditioned environment for custom ventilation, and I would think the epoxy would have a lot of fumes, but it says
yes, that is true. But I would say all stereolithography printers come enclosed, whereas not all FDM printers come enclosed, and so for that reason, I think they're mentioning those or highlighting those differences. Good question.
I would imagine that there's less warping in the process with the SLA and the FDM. Is that true?
Yeah, the warping tends to be from the heating and cooling of a part. And so you're constantly battling that with FDM. You want certain parts of it to be really hot while other parts you want rapidly cooling. Stereolithography is a cool process. I mean, right at the interface that you're curing, it gets really hot, but then it cools right back down because of the resin bath. So you're not dealing with warping nearly as much, or maybe even hardly at all. Mason, did you have a question?
Yeah, I was just gonna ask if the FDM is significantly less expensive to purchase than the SLA.
It is. So SLA printers, like low end, they start at about $2,000 and go up to $10,000+. Whereas FDM, you can go as little as we'll see here in a second, but like $200 or $300 will get you started with an FDM printer, and then they can go up to I don't know, $5 grand, $6 grand, but they also cap out lower than SLA. So yeah, FDM is generally not only cheaper to begin with, it's cheaper to maintain. Dan.
That was kind of dovetails in my question about what kind of maintenance these two systems require, and like, you know, durability and kind of ruggedness. I assume it depends on the quality of, you know, which unit you purchase, but
Yeah, that's a good question. So SLA, because you're dealing with resins, there's a lot of cleanup involved. And so FDM is a more, let's say, plug and play with less post-processing. But SLA, because you have less moving parts, the motors, the belts, and the various, you know, joints and axes, it has less things breaking, or maybe less maintenance in that respect. So they both have their idiosyncrasies. And obviously, if you're willing to buy a you know, top dollar machine or something more expensive, then that maintenance also goes down. SLA is, I would say, of the two, SLA is definitely more involved. Post-processing, cleanup, daily use, daily maintenance. SLA is probably more involved. Cool.
So Brett, one last question for me is, the SLA, can that resin that isn't fused, that's still in the tank, can that be used again? And what kind of a shelf life does it have?
That's a great question, and it's probably resin dependent. I don't have a whole lot of direct. We have a FDM machine at Luxel, and so I don't have much direct experience with SLA. But I would imagine there's a shelf life to those resins for sure.
I think so.
Most resin printers come in or I would say a lot of them come in a UV blocking box, and so that resin isn't being quickly cured by, say, outside light, and so you can print multiple prints off of the same resin bath. Dana, go ahead.
Is there anything like lacing, you know, with the SLA? Is there anything weird that happens with that, or is that only with the FDM? It seems like some things I've gotten are, you know, they just, when you go thin, they just look like wood grain, kind of with the sapwood taken out. Like
the texturing or something like that?
Yeah, like it doesn't quite fill in in a lot of places.
You won't see that with SLA. Yeah, you can't see the grain boundaries or the layer boundaries with SLA. And that's, again, kind of part of the curing process. The XY resolution of an SLA printer is, yeah, I want to say it's well below 100 microns. And so the spot size is really fine. And then the layer resolution is also less than 100 microns. So you're not going to see those layers. Let me show you just some well, the pictures are up next. Go ahead, Bill.
We have restrictions on the angles and the orientation of a hole, for instance, with the FDM, but the SLA, I'm wondering, does that make any difference?
Yeah, it definitely does. Printing with support structure and getting rid of it is well, you have to print with support structure with SLA because the print bed is upside down, right? And so for that reason, and just by nature of the orientation of that print bed, you are going to have to account for different things in your design.
Okay.
Yeah. So here's a list. It's certainly not exhaustive, but here I'm highlighting, you know, SLA. You have, I think, a much broader range of what you can print with. You can print elastics, high temperature resistant materials, which you can't do with FDM. Most FDM thermoplastics, they melt in the upwards of 250 C range, 300 C, because they have to go through a melting and resolidification process. You can print though with things like nylon and PETG. Even ABS is a pretty high performance plastic, and so you can get some really quality products with the materials associated with FDM. Just to give you an idea of what it looks like to print the same part with both printers. This kind of gets at your question, Dana. Much harder to see the layer resolution out of the SLA on the right, whereas on the left we have FDM, and you can definitely see the print lines. One more here, just as an example. Both are great and can be used for a wide variety of things. Like I said, we have an FDM printer at Luxel, and we use it on a weekly basis, if not daily sometimes. So FDM certainly has its place. It's cheaper. It's fairly plug and play, and it's a great form of 3D printing. So because SLA, I would consider SLA to be more involved. And also it's a bit more expensive. I wanted to just focus, for the sake of going through this selection process, I wanted to focus on just FDM. Even within the FDM world, there are many different styles and types of printers. And what it comes down to is how the printer knows where the nozzle is at, okay? So there's Cartesian and polar, and then that informs how it's spec'd and what the hardware looks like. So here we're looking at a Cartesian printer. The components move linearly along an X, Y, and Z axis, okay? The pros to a Cartesian printer like this is it's inexpensive, it's pretty simple to understand, and it's for that reason it's easy to fix or upgrade. And this is kind of the bread and butter type FDM desktop printers. So there's a lot of support out there. There's hundreds of forums, and it's something a lot of people know a lot about. So if you're getting up and running, this is a great place to start, because you can go out and get your questions answered online. The cons is that it is a rather bulky frame. It is relatively slow, and you're limited to your build volume. Not much else to say there. You're also, I would say, with a printer like the one shown here, things like bed leveling and temperature, you're constantly fighting the temperature of your filament. Sometimes, because you want it hotter in some places, colder in others. Experimenting with fans, troubleshooting so that you get the type of print and the quality of the print that you want, that can be kind of cumbersome. So I would add that also as a con to this particular type of printer. We're not going to look at any polar in the next two examples. We're not going to look at any polar coordinate printers, because they're so few and far between. They're, I think, unnecessarily complex in their mechanisms, and there is not a lot of support for them out there for troubleshooting and whatnot. And so I just didn't feel like this was a space to maybe look at those. We have the Delta printer. It's a little bit different than the one we just looked at, in that there are 3 or more arms that are attached to these vertical rails, as you can see here. And these arms move up and down on these rails, and they're hinged at the center. And so you can effectively move the print head anywhere down on this build platform by both hinging and moving the wheels here on the vertical rails. The pros is that it's relatively fast. You have a high print quality, based on the hardware and the mechanics and the design. And these typically you can get taller prints on, but a smaller XY print area. Cons, difficult to fix or upgrade. And they're typically a smaller, like I said, XY axis. Direct drive extrusion. They're less compatible with direct drive, which I believe is when I have to double check what that actually means, but I believe it's when the filament comes in from a spool that's mounted on the printer. Then we have Hbot printers. Okay, this exact printer is the one that Luxel has. These use belts to move the print head within the XY plane. So there's belts that run along the top sides, both directions. Okay, and the print head will run across an x-axis gantry, which is this bar here. And that gantry will move along a y-axis gantry as well. Some other bars going this direction. You can actually see it right here. The pro here is there's a relatively large print space. They're also, the Hbots are all encased and have a pretty robust support structure. And so you have, they're stable, there's fewer vibrations, which can help with print quality. And they typically are built larger for that reason as well. So you can get larger prints. The Hbots tend to be relatively more expensive, at least in comparison to other Cartesian printers. They're large, so you need maybe a designated desk for them. And there's less support because, for example, this particular printer has its own forum, but because of all the hardware and whatnot, you have to go directly to that forum to troubleshoot or fix something if it goes wrong. Whereas if you were to build your own or have more of a printer like this one here, there's say hundreds of forums that you could go on and look and understand maybe what's going wrong here. So what do we do? How do we select the right printer? So this is a method that I want to share with you guys because it's how I chose the printer for Luxel. This is a method that I learned in college, actually from a materials teacher. And it was used, or at least it was taught to me, in how to select a material from a number of materials for a specific application, how to choose the best material, let's say. But this is a method, the comparison matrix method, CMM. It can be used for really selecting anything. It's a quantitative selection approach for choosing the best possible option on the basis of several defined parameters. So our objective right here is to evaluate the best of 5 FDM printers on the basis of 4 metrics, okay? The process itself, and this will make sense by the time we're done with this, and then you guys will have a chance to actually work with your small groups on a practice problem. But step 0 is going to be to define the parameters and metrics by which you're going to measure these printers, okay? So you're gonna come up with that. They're gonna be predetermined. And part of it, most of it's gonna be driven by what you want out of a printer. Let's say, for example, you have a budget. So cost is gonna be a parameter by which you're gonna evaluate these. And then maybe materials is another. We'll get into parameters in a second, but we're going to define those first. Then we're gonna set up the matrix, and we're gonna apply weighted values to each metric. So let's say, once we have 4 or 5 metrics, which one is more important to us is essentially what that's doing. It's gonna apply a weighted value to each thing that we're concerned with. Then we're going to go through and grade each printer for each one of those parameters. Once we've done that, we're going to multiply by the weighted value that we determined for each parameter. And at that point, we're going to have essentially a total score for each printer that's going to systematically narrow down maybe our top two or even one. And this is a really nice unbiased way, I think, for selecting, or evaluating something. And it's okay if this all doesn't make sense right at the moment. We're gonna cover it in good detail. So the printers we're gonna look at, these are, I've chosen 5 printers that I would think are within the realm of possibility for a hobbyist or any one of us maybe interested in buying a printer. And they range from $200 to $1,200. Okay. Hobbyist printers can get up to in I would say the $3,000 or $4,000 range, but we've kept it to $1,200 for this example. The parameters that we're going to focus on are going to be cost, the print volume, the ease of use, and the material capabilities. So what all can it print? I will say that when it comes to ease of use, that's a little bit more, it's not as concrete, if you will, when it comes to evaluating. And we'll talk about maybe how you would come up with a value for ease of use when we get there. There are many other parameters that we can use to evaluate printers. And before I maybe pop the list up here, does some people want to chime in what they think you could have as a parameter?
Size of the actual machine.
Sorry?
Size of the actual machine.
Size of the machine, yeah. So what space are you working in, and how much space can you afford? A few others.
About ability to fix it if anything goes wrong.
Yes, absolutely. So serviceability, yes. Thanks, Mason. Let's get 2 more, and then I'll pop up the list I have. And I don't think I had either of those on my list, so it's good we're doing this.
My big one is resolution.
Resolution is a big one, absolutely. One more?
I'd have to say your ability to reach out to other people.
Yep. The yeah. What would that even? I don't know how that. What would that be called? But you're absolutely right. Support. Yes.
Community. Yeah.
Yep. You got it, Bill. And good one there, Dana. This is not an exhaustive list. Cost, print speed. We already talked about those first 4. Whether or not it's enclosed. Repairability, that's kind of serviceability, what Mason hit on. The build volume, accuracy, durability, the number of extruders, okay? So some printers come with multiple extruders, and that can allow you to, say, diversify your applications. Cost of upkeep, HEPA filtering. Some of them come with HEPA filters. That can be nice if you're printing nasty plastics. A lot of plastics just smell bad anyway. And so it's nice to have that all encased, and you don't have to build your own, filter system or whatnot. And many higher end ones come with built-in cameras as well. So you can remotely log into your printer, start a print. You don't have to be around, and then you can watch it as it's printing to assess if, it's printing right, or, so on and so forth. So lots of different things we can assess this on, and it's not an exhaustive list. You're going to get, I would say, more accurate in your results, or maybe a more thorough search if you were to expand your matrix. We're only looking at 5 printers and 4 parameters. You could make this matrix, 20 printers and 30 parameters. And at that point, that you'd be narrowing down to the absolute best possible choice, given your set of parameters. Yeah, Bill.
Question about the enclosure. I'd thought an unenclosed one, which might be a little cheaper, could easily be enclosed with like a plexiglass box that you would just drop down over it, something like a bell,
Yeah.
Is that feasible, or is there something about the enclosures on ones that are enclosed that that kind of an arrangement wouldn't deal with?
No, you're absolutely right. In that you can, with any of these printers, right, you can buy the core pack or the core printer itself and then build and mod on top of that, right?
Okay.
So yes, I think that would be perfectly feasible to buy a cheap printer and then build your own enclosure for it.
Good.
All right, so let's get started. Step 1, we're going to apply the weighted values to each one of our parameters, okay? And the reason we're applying weighted values is so that, we have, let me actually open or pull this over. First of all, just to give you an idea of the printers that we are assessing here. We've got the Creality Ender 3 Pro 2. So this is one that is not encased, okay? This is like the Cartesian printer we looked at. We have the Flash Forge Creator Pro 3D, okay? It is encased. It's also Cartesian. This is more like the Hbot, and that's the 6 printers that I have back behind me. That's what they are. Just a sec, I've got the zoom bar right there. We are gonna also look at the Dremel 3D 20. Already had that up. All right, and then we're gonna look at the 3D Walks 1 and the Flash Forge Adventure 3 Lite. So like I said, the first thing that we are going to do is apply weighted values, okay, to each one of our metrics. So we have cost up here, print area, print height. Now I've segmented both print area and print height because those to me are 2 different parameters. You could potentially put the 2 together and just assess it based on print volume, but I don't think that gives as accurate of a representation of the perimeter limitations, let's say. So print area, X, Y, and print height. Then we also have ease of use and material capabilities. So you can see that I've defined each parameter or the metrics for the parameters on the second row. So for cost, for example, we're going to assign values 1 through 10, okay, with 1 being the most expensive. So it's going to make the value of the printer go down in our selection process, and 10 being the least expensive, which is a good thing. So we want that to increase the value of our printer in its overall score. Print area, we're going to assign a 10 for the largest and a 1 for the smallest, okay? Because let's say, in this case, we want the maximum build area, right? We want the most flexibility. So score will go up as the area increases. Mickey, go ahead. Oh, you're muted.
Can you zoom in?
Oh yeah, I'm sorry.
On my screen, it's very tiny.
Yeah. Let's see here. Better? Better, okay.
Easier to see.
Print heights is kind of the same thing as print area, where the higher and taller we can go, the better. And so we want to increase the score for that. So 10 for the largest, 1 for the smallest. Ease of use, 10 for the easiest, 1 for the hardest. Material capabilities, I've gone through and I'm going to assign a value of 3 if it can print less than 5 materials, 7 if it can print between 5 and 7 materials, and 10 for if it can print greater than 7 materials. Okay. Now, we also want to apply weighted values to these. So in this case, and the reason we're going to do this is if the most critical of the parameters that I'm concerned with is in this case material capabilities, I want to weight the score for that more heavily than say ease of use. Okay, as some so that's I'm going to weight that at 0.35. So 35% of the overall score is going to come from material capability. And then we've itemized it down as well. So cost, also really important to me. We're on a budget. So 30% of the weight in the score is going to come from cost. So on and so forth. So this, I would say both the parameters and the weighted value is personal to your end goal with the printer. Do we have any questions so far?
Yeah, those weighted values are not, they don't add up to 100. They're not a percent, correct? They're just a weight.
No, they are a percentage. They do add up to 1. So here's my double.
Oh, they do. Okay.
Here's
I
my
didn't
double
do
check
that.
here. My double check is a summation of these rows. And so yes, I would say it's very important that they add up to 1. So you know that you're scaling properly in this analysis. Yeah. Thanks for highlighting that. Oh man. All right. So we've done step 1. Step 2, we're gonna, well, before we grade, we actually have to go in and input the metrics, okay? So this is the most time-consuming part of this process, and that's where you go to each one of these pages, right? And we scroll down to their technical specifications, and we might have to do some Google searching, some digging, so on and so forth, to find the information that we're interested in. Okay, so I've popped each one of these up. We're not going to go through and physically find all this information. I've already done that. But most websites are going to have something like this, right? Labeled specifications, and then they're going to have things like print speed, maximum temperature, the number of materials that you can print. So what you do is, or at least, what I did was I opened up another sheet. We have our 5 that we're interested in, and then we do all of our research. We input all of these values. So the Creality Ender Pro 2 is our cheapest printer at $215. Our Cindo 3D WOX is our most expensive at $1249. Associated print areas, print height, ease of use, material capabilities. Are there any questions on that step? Okay, makes sense. Then you're gonna grade them. This is where it can maybe be a little bit tricky in how it's analyzed. And I would say there are 2 ways you could do it. The way that I did this particular one, because I think it's more straightforward, is I assigned a value of 10 to in the cost column to the cheapest printer, okay? And then I proportionally scaled the rest of the scores based off of this one, okay? So what that means is, for example, for the FlashForge Adventurer, I did 295 divided by 215 to get some factor relating the cost of the FlashForge and the Ender Pro 2. And then I multiplied that factor by 10 to get the associated proportional scale, value for the FlashForge Adventure 3 Lite. Does that make sense? The other way we could do this is we could linearly interpolate. So you'll see that I don't have a value of 1 for the most expensive printer here. So what I would do is I'd assign my value of 10 to the least expensive. I'd assign my value of 1 to the most expensive, and then I would use mathematics or linearly interpolate each of these values or costs that are in between. We're not going to do this particular one that way because that requires some it's more involved and some mathematical background that I didn't want to get into. So we've proportionally scaled each one of these. Does that make sense? Do you want me to go through one of the calculations to show you, or do people feel good about it?
That would be helpful for me if you're willing to, and if everybody else is willing to wait. But
yeah.
Otherwise, it's okay. I can do it later with you.
No, I'm happy to. Let's do it. So let's focus on the cost of the Dremel Idea Builder. Okay. So we've already assigned a value of 10 to our Ender Pro 2, so that is the one that we're going to compare it to. So over here, I'm going to take the cost of the Dremel Idea Builder, and I'm going to divide it by the cost of the Ender Pro 2. Okay, so we know that the Dremel Idea Builder is 3.15 times more expensive than the Pro 2. So it should have a value that is 3.15 times smaller than 10, right, to get the scaled score for the cost in our analysis. So over here, we're going to do 10 divided by 3.15? Yeah, close enough. And we now have a value of 3.17, 3.16 as our score for cost in this analysis. Does that make sense, Mason?
Yes, thank you very much.
Yeah. Because it's kind of an inverse relation here with cost, because the least expensive gets the highest value. I'll do one more example with print area, okay? So we've assigned a value of 10 to the 3D WOX, which has the largest print area of 42,000 millimeters squared. Okay, so if we want to come up with the score for both the Pro 2 and the Adventure 3 Lite, which have the same build areas, we're going to do 42,000. And this can be done on a calculator, but I'm just going to do it here. Divided by 22,500. So we want, if we're giving 3D WOX a value of 10, we want to divide 10 by 1.866. That's the scaling factor to come up with the score for the Ender Pro 2 and the Adventure 3 Lite in terms of their print area. So 1.866. So if we go 10 divided by 1.866, we get 5.36 as the print area value for these two printers.
And you just do that for everyone other than the 10.
Yep, exactly. You assign your value of 10, you proportionally scale the rest. Okay, this is your top choice, and so you're giving it the highest value effectively, and then you're scaling the rest. And like I said, linear interpolation might be a more accurate way of analyzing it, but this is sufficient. This will work just fine. Cool. All right. If people aren't understanding that, please let me know. I'm happy to go through this more. Otherwise, we'll keep on. We're nearly there. We've done the I would say the hardest part.
I have a quick question. Are we
Yes.
gonna create our own parameters? Like, even though they're different, yours are different than mine? Am
Yeah.
I putting my parameters? That's what I'm doing on that.
I think, yes, I think you should take this home and create your own, absolutely. For the in-class example, you're gonna tweak what we've done here. I thought that would be easier for, like, say, class discussion. But absolutely, you should come up with your own list of parameters and metrics for your own, decision process. Okay, so we've done steps. Oh, we're not done with step 3. So once done grading, which we've done here, this was the grading where we assigned a value of 10 to the best and scaled. So that was the grading step. Once we're done there, we're going to multiply that grade by the weighted value. Okay. So let me pop this screen up again. So this is fairly straightforward in that at the very beginning, we applied a weighted value because cost and material capabilities meant more to us than ease of use, print area, and print height, right? So we went through and we did all that. Now we have to apply that weighted value to each grade. So for example, the Creator Ender Pro 2 had a value of 10 as a grade, and we're gonna multiply it by 0.3 to get an overall final grade for cost of 3.00. Okay. Over here for print height, only 7%. We're only concerned with this about 7% of the overall grade. So 7% times what were we looking at? The Adventure 3 Lite, or no, Creator Pro. So Creator Pro 0.07 times 7.5, right? So that was the original score. We multiplied it by the weight. And so that comes out to be 0.525. You go through that, which it's somewhat arduous by hand, but if you're able to create a spreadsheet and associate values, it can be fairly quick. Once you've done that for your matrix, you're gonna sum up each score for each printer. So the Creator Ender Pro 2, 3 plus 0.4288 plus 0.7 plus 1 plus 1.05, and you have a total score of 6.1788. Okay, you do that for the rest of them. And so we've taken what was an overwhelming number of options, not in this case, but there's hundreds of different printers out there. There's all these different parameters to think about. We've taken what was an overwhelming idea and systematically came up with a best option on the basis of what's most important to us. Okay, so the Flash Forge Adventure 3 Lite, which happens to be it's not the least expensive, but it's one of the cheaper options. If we go back and look at our metrics, it's the second cheapest at $295. It has the highest score, so that's going to be the best option for us, given how we set up our matrix. And then there's the Creator Pro just beneath it, so on and so forth. Now you don't have to take this score and as the end all. I mean, it is accounting for everything that you are concerned with. But if you wanted to, if you're like, man, but the Creator Pro is encased and has a webcam, then either you go back and redo your matrix, including those, or you say, yeah, okay, I'm going to get the Creator Pro because it's the second best and it has some of these other features that I want. Are there any questions on that? Does that make sense?
You can do this with anything. You can do this with new shoes.
You
can
can
do this with lumber. Anything you want.
I do it with a lot of things. I do it to evaluate players during tryouts at soccer. It's a very unbiased approach. Yes, you're right, Mason. It's a great approach to evaluating something, anything. So what we're gonna do, we did steps 4 and 5. That was just adding up all the weighted scores and evaluating based off of that. You should see in your email, okay, this assignment that we're gonna break out and do. It's 809. You know what? Yeah. Do we have time for that? Shouldn't take that long. We'll give it a shot. We'll go for 15 minutes and see how it goes. And then I'll wrap us up at the end. But we're going to evaluate the same 5 printers with the same parameters and metrics, okay? So not much is changing about this, but as a group, you're gonna change the weighted values, right? What's most important, what's not, and so on and so forth. And how does that affect your overall results? So what you're gonna get before you dive into it is sorry. You're all gonna see this, okay? What you're gonna wanna do is put in, as a group, put in the weighted values, and they have to equal up to 1, okay? And then I would say delegate 1 column to each person. 1 column to each person, and they're just gonna multiply that weighted value by the score that we've already given the printer. Okay, so if this is 0.4, let's say cost is really, really important to you, maybe even 0.5. You're gonna do 0.5 times 10, 0.5 times 7.2, so on and so forth. So 1 person will do that, 1 person will do that, so on and so forth. And then you guys as a group will sum. You're gonna work with the first printer here and sum across each of those values that you've come up with. And at the end, you're gonna see if the results are the same as what we had before, or if maybe a printer has swapped places with another based on your weighted value change. Cool? Any questions there? Yeah, Dana.
Did you send that? Maybe I just looked at it wrong, but I thought I got a PDF instead of an Excel.
Oh yeah, sorry. It is a PDF. I thought I had emailed, bring a pen and calculator. If you have a piece of paper, all you'll really be doing is writing down 1, 2, 3, 4, 5 values. Not everyone's on Gmail, and so sending out Google Sheets or what? I guess I didn't do that. Cool. Good to go. I'm gonna stop sharing. You guys have, let's say, 15 minutes to work as a group, and I'm gonna open the rooms now. Chelsea, I was asking, were you talking in reference to the die casting job that you had? Yeah.
Oh, so many of them, but yeah, die casting was a big headache.
Yes. I mean, I don't know the ins and outs of die casting, but I can imagine.
Yeah, one day over drinks in the future, maybe I'll talk with all y'all about the project, but
yeah. It was that bad. It requires a few drinks, huh?
Yeah.
In order to get the geometry they wanted, they put the whole piece after it was manufactured on a belt sander, which created sharp edges.
Oh boy.
Oh, great.
And it was a consumer product.
Wow. Yeah, that's brutal. And I'm guessing you were making a high number of them, whatever it was. Die casting is generally high throughput.
Yeah, 5,000 of them.
Wow. All right, you guys. So Sam, if you want to share the results that you got, maybe share the weighted values and then the top one and the or maybe just the I guess all the printers and their associated values.
Yeah. So we weighted. One sec.
Or just say what you most heavily weighted, I guess, and what you least heavily weighted.
We most heavily weighted cost, and we least heavily weighted print area on XY.
Okay.
And we got a result of the Flash Forge Adventure 3 Lite was our highest valued printer, and our lowest valued printer was the Dremel Idea Builder.
Okay, cool. And group 1 had a similar outlook. Let's see here. Change score example. They, Chelsea, you want to tell the group what you most heavily weighted?
Sure. We heavily weighted cost and ease of use the same at 0.3. And least was material capability at 0.15.
And
I don't remember the results, sorry.
yeah, that's okay. I have them. And the results of that was the Flash Forge Adventure 3 Lite at the top and the Dremel also at the bottom. So similar results for the top and bottom. And I guess the point and what we're going to wrap up with here is we've associated, at this point, we have 3 examples with different weighted values. And there's a trend as to the Adventure 3 Lite has been at the top or in one of the top 2 positions each time. And the Dremel has been at the bottom each time. So what that means is the Adventure 3 Lite is pretty robust in its scoring in each one of the parameters, not just one, because we've weighted each parameter differently 3 different times. So this is a pretty thorough analysis that shows that the Adventure 3 Lite, based on all of these parameters and weighted differently, is the best selection out of these 5 printers in this example. So
it's good.
We could, you know, and I'd recommend if you're designing or selecting any machine or anything, but if you're looking to pick up a 3D printer, expand this matrix, look at more printers and look at more parameters and take your time with that. And once you run it through several different iterations with weighted values, you're going to see that some printers shift towards the top and some shift towards the bottom. And that's the top few are what you're looking at making your decision on. Cool. So we're a little bit past 8:30. Appreciate that. We have one more class. This has gone really, really fast. It feels like to me. There's more I'd love to cover, but for this coming week, I would say your main focus should be finishing the project by Sunday. Okay, at least one of them, and then the tutorials and stuff you can finish even beyond the class. I'm gonna complete those tutorial videos, and it seems like that's been pretty autonomous for you all. And so to me, it would be more important as a class to focus on, or at least to prioritize finishing your projects by Sunday. If you get stuck, let me know. I'm happy to help. You know, push you right along with those projects as well. And submit them by Sunday night, 12 p.m. or really any time when I wake up is when I'll look at it. Cool. I'm trying to think if there's anything else. I haven't decided yet. I will say this. Next week, I don't have a whole lot of new stuff I want to cover, but I do want to do a bit of review and answer questions. And I also want to create some space to show forums that you can look at for Fusion and some other tools that you can use yourself to kind of further your skills. So that's my plan for next week. As a part of review, I haven't decided yet, but I might put together a Kahoot trivia. I mentioned that like first class. And so I'll send out the instructions for downloading Kahoot on your phone, okay? You need to have your phone app open, and then the questions will be presented on Zoom, and then we'll all get to interact through a trivia game. So I'm thinking I'll do that if there's time. So please download that on your phone beforehand, just in case we do.
Brett,